Well, all right. This is problem 6.59 from the other textbook. Um, and it's the ride, and you've probably seen it. I don't know, they don't have it at Great America anymore, but they have it at other fairs. The Gravitron 5000, sometimes you see it called. Spins around and you get pinned against the wall. Okay. And they ask you to prove that the maximum period necessary to keep the person from falling is t equals 4 pi squared r mu s over g to the 1/2. So first we got to prove that. So to do that, we're going to make a free body diagram viewed from the top. So we're going to view it from this angle. So that's the view from the top, and the person is here against the wall. Okay. So if we look at the free body diagram, it's going to look like this. We're going to have so there's going to be a force coming inward, and that force is going to be the normal force. Okay. So as the wheel spins, okay, like this, we're going to get a normal force that comes in. And now if we look at it from the side view, like again, I'm looking at it like it's a box. That's a terrible box. But you get the idea. That's what it looks like from the side. If I just looked at it and I couldn't see there was a top and a bottom circle. Okay. That force diagram is going to look like this. Okay, I'm going to have that normal force still going in. And I'm going to have mg going down. Okay. And in order to, I'm going to, again, this is a static friction against the wall, and that's going to go the opposite direction. It's going to go like that. I'm going to call it static just to remind us that it's static. Okay. And if you look at the equations, okay, we'll have to make two. Because remember, the static and the mg hopefully are going to be balanced, otherwise it's bad times for the rider. So we're going to have Fs minus mg equals 0. And we're going to have the normal force is going to be ma sub c. Okay. And again, since we're dealing with period here, rather than use v squared over r, I'm going to replace this with m 4 pi squared r over t squared, where t stands for the period. Then we're going to do some substituting in just to make it a little bit easier. We'll start by rewriting the formula for rewriting the vertical formula with mu f of n in it. Maybe. There we go. Mu f of n. And that's got to equal mg. I put it on the other side. And we can replace f of n. We know that's going to be mu. We know that has to equal m 4 pi squared r over t squared equals mg. Those divide out. I actually call this S because we know it's a static friction. Okay. I want to keep those in there too. And we have to find the period, so I'm going to move this to the other side, move that to the bottom. So we have 4 pi squared r mu sub s over g equals t squared. And you can see we just take the square root of both sides, and we get 4 pi squared r mu s over g, which was our goal all along. So good for us. All right. You can see that the bigger the radius, the bigger the period that we're going to get, but that it's dependent on the square root of the radius. So if we want to double the period, we need 4 times the radius to go around. So that's interesting to think about. Also, the rougher the surface, I know it's not really physical roughness, but the more frictiony the surface is, the more the greater the period can be. We don't have to spin it as fast. If it's the smoother, the less frictiony the surface is, the faster we have to spin it, the smaller our period has to be. That matches up with what we're thinking too. For B, they say if the rate of revolution is made to be larger. Okay. So that means that our period is going to end up being, smaller. Okay. What's going to happen to each of the forces? Okay. Well, if I have a smaller period, okay, that means that this force here is going to, the normal force is going to end up being larger. Okay. That's down here. Okay. So I made the rate of revolution larger. That makes the period smaller. And that means that this normal force piece here is going to get a lot bigger. Okay. Because it's going to spin faster, right? So it's going to pin you against the wall stronger. So the normal force will get bigger. Okay. Well, even if the normal force gets bigger, that means that the frictional force that's possible gets bigger. But the only force that's countering it against is going to be the force of gravity, right? So think about it like the same way you think about the block sliding. You know, if you start sliding an object, it'll pick up frictional force until it reaches that maximum. As long as you don't reach that maximum, it's not going to make any difference. So it shouldn't change the static frictional force because it isn't changing mg. You're still going to be balanced there. So our person here is in good shape. They are not going to slide at all. So good for them. We're glad to hear it. They're staying where they are. Okay. Good times. Okay. Now the next question asks, what about if the rate of revolution is made? If the rate of revolution is made smaller. Okay. So now in that case, you can see what's going to happen. If we make the rate of revolution smaller, period is going to be larger. Okay. And that's going to make this number larger. That's going to mean that normal force becomes smaller. That sort of makes sense if you think about it. And that's going to, because it's not going to spin as fast, so it's not going to pin the person against the wall as strongly. Okay? And since the person's not going to be pinned against as strongly, there's going to be less frictional force because this number got smaller. And we said last time that even though the frictional force is bigger, it won't make, this time it's going to be less than the amount needed to match mg. So now we're going to have a smaller frictional force, but we're going to have the same mg. So she is going to accelerate down that way. Bad times. That's not what you want to have for your ride. Your liability insurance carrier not going to be excited about that. So she's going to accelerate down the ramp. So that's how the motion changes. And that's the end of problem 6.59.